In question 2, we're now looking at wind turbines. So we're told we've got a wind farm, which is obviously a collection of wind turbines, and that they must have, in this case, a minimum distance of 500 meters between them for maximum efficiency. Okay, and then in the diagram underneath, we've got a little bit more information about how 9 of those wind turbines are positioned. Now, what the question wants us to do first of all is to suggest one way in which this layout ensures the maximum efficiency when the wind direction changes. Alright, now the key to this is that you will want to face your wind turbines. You'll actually want to turn them around so they're pointing into the wind so that the blades of the turbines catch the maximum amount of wind. Okay, and the way that this layout helps with that is that you can see, if we look at this wind turbine here, we can draw a circle around it, and whichever way that wind turbine is facing, we've still got that 500 meters of clearance that we need for maximum efficiency. So whichever direction, we've still got the 500 meters that we need. Okay, so what we need to do is just translate that little diagram there into some kind of written answer. Okay, and a sensible sort of way of writing down that is to say that the minimum distance between the wind turbines is at least 500 meters regardless of which way the turbines are facing. Okay, so that would give us the mark we need for that part of the question. In the next part of the question, we've got some more information. We're told that the average mass of air passing through the blades of one wind turbine is 51,000 kilograms per second. Okay, we're also told the density of air, and the next thing we've got to do is to recall and write down the equation for density. Okay, so in words, the density is equal to the mass divided by the volume, or in symbols we have the symbol Greek rho for density and mass over volume. Okay, either of those would be acceptable. And then 2.3, we need to calculate the volume of air that's passing through the blades of one wind turbine per second, and also to remember the correct unit, and we've also got to give our answers to 2 significant figures. Okay, so things that we need to do. Okay, first of all, I'd like to take the equation I had for density there and rearrange it to tell me that the volume is going to be equal to, if I take the volume onto that side, the density will go down there, it's going to be the mass divided by the density. Okay, so I know that the mass of the air per second was 51,000, and that then needs to be divided by the density, which was a 1.2. So running that through my calculator, that tells me that the volume of air is 42,500, and because I've used kilograms and kilograms per meter cubed, the units are going to be meter cubed for volume. So I've calculated the volume of air, I've given the unit. What I still need to do is to give my answer to 2 significant figures. Okay, so my first significant figure is a 4, then I've got a 2, and then because my next figure is a 5, when I do this to 2 significant figures, maths, I need to round up. So instead of going to 42, I go up to 43. Okay, so that's going to be my final answer when it is rounded to 2 significant figures, and then all I would do is transfer the 43,000 into there and the meter cubed into there for my final answer. Okay, so there is my volume filled in, rounded off to two different figures, and there I've stated the units that I've used. Alright. Now, 2.4, we're told that the average power output from one of the wind turbines is 1.6 times 10 to the 6 watts, and we've then got to make a comparison to a nuclear power station where the average power output is 2.4 times 10 to the 9 watts. And what we've got to do is to calculate the number of wind turbines needed to generate the power equal to one nuclear power station. So what I know, the power from an average nuclear power station is 2.4 times 10 to the 9 watts, and each wind turbine gives me 1.6 times 10 to the 6. So if I take my 2.4 times 10 to the 9 from the nuclear power station and divide that by my value for one wind turbine, that will tell me how many wind turbines that I need. Okay, so the trick with this question is being able to use the standard form notation on your calculator. If you can get these figures into your calculator correctly, then your calculator will tell you correctly that you need 1,500 wind turbines to match your single nuclear power station. And the final part of the question is that the UK requires a minimum electrical power of 2.5 times 10 to the 10 watts, and we've got to give two reasons why wind turbines alone are unlikely to be used to meet this requirement. So this is basically saying, why don't we just use wind turbines to try and meet all of the UK's demand for electricity? Okay, so the obvious thing about wind power is that it is unreliable. Okay, on a day where there's no wind, or where there's only a little wind, we're not going to get enough power to meet that demand. And the word unreliable is the key word that we'll be looking to show there. Okay, now the second thing that we could say from the calculation that we've just done, we could see that we needed 1,500 of those wind turbines to meet or to match what one nuclear power station would produce, which is again another factor of 10 smaller than what the UK actually needs. So we could do a calculation to see exactly how many wind turbines we would need to actually meet this figure here, and we'd need an awful lot of them. Okay, but it's fine for us just to say we would need a very large number of wind turbines. Oops. Okay, so we could get away with saying that in words, or we could actually do a calculation to see exactly how many wind turbines that would be needed, and if you did that calculation, it would be something like 15,625. So indeed a very large number.